Let's review solving problems using conservation of mechanical energy. 1. Take 2 snapshots of the system. 2. Calculate the various energies, kinetic energy, gravitational potential energy, and elastic potential energy for each snapshot. And here are the equations that I would recommend you memorize. And 3. The sum of these, that is the total mechanical energy for one snapshot, equals the sum of these for the other snapshot. So let's use this conservation of energy procedure to solve this problem. Actually, we're going to do this problem twice in this lesson. First with variables, and then secondly just putting the numbers in. We have a cat that sits at rest on a window ledge in an apartment building 1.1 meters above the floor on the 13th story. The floor level is 41 meters above the street. There's our cat. The cat is a certain distance above the 13th floor. I've represented that by H1. The floor is 41 meters above the street. I've put that dimension line in here. There's the street, and all the way up to the 13th floor, that's height H2, which would be 41 meters. Find the speed of the cat landing on the floor. The cat is going to jump off the windowsill and land on the floor. What's the speed of the cat just before it hits the floor? We know that the initial speed of the cat is 0 because we're told in the problem statement that the cat sits at rest. So his initial speed, VI, is known to be 0. So we need 2 snapshots of the cat. One when the cat is on the windowsill, and one right before it hits the 13th floor. Let's define that floor level as being the reference line. Snapshot A will be when the cat is in the window, and snapshot B right before he hits the floor. The cat doesn't have any kinetic energy in snapshot A because he's at rest. But relative to the reference line, he does have some gravitational potential energy equal to his mass times g times his height above the reference line, which would be m times g times h1. We don't have any springs in this problem, so there's no elastic potential energy to worry about. Now the cat jumps off the window ledge and is just about to hit the 13th floor, falling down 1.1 meters. He will have kinetic energy. That will be 1/2 times m times his final speed squared. Since we chose the 13th floor to be the reference line, essentially at snapshot B the cat will be at the reference line, which means his h will be 0, which means gravitational potential energy will be 0. Again, no springs to worry about. And then the conservation of mechanical energy idea says that the sum of these 3 terms must equal the sum of those 3 terms. Well, those are fairly easy to add up and set equal to each other. It turns out that in this case the mass of the cat is irrelevant. Could be a skinny cat or a really fat cat. Makes no difference. So I'm going to divide both sides by m. GH1 is equal to 1/2 times VF squared. If I solve that for VF, this is the expression we get. Multiply both sides by 2 and take the square root of both sides. And now we just put the numbers in. Make sure that we do this product underneath the entire square root sign and then take the square root of that answer, 4.6 meters per second. Let's do it again, but this time we'll just pop the numbers in. In snapshot A, remember this is when the cat is on the window ledge. He's not moving, so he has no kinetic energy. But he does have gravitational potential energy equal to his mass times g times his height above the reference line. No springs in this problem. Snapshot B, when the cat is just above the floor, he will have kinetic energy because he's moving at that point, and his kinetic energy will equal 1/2 times m times VF squared. Because he's essentially at the reference line, he won't have any gravitational potential energy, and we have no springs. So now we're going to total up all the mechanical energy for snapshot A, total up all the mechanical energy for snapshot B. 1/2 times 7.4 is 3.7 VF squared. Those two quantities are equal to each other. Divide both sides by 3.7. Take the square root of both sides. Look at that, just what we got before.